programming FPGA boards in Verilog with Tina. In our other videos, we've shown how you can create a digital circuit and download to an FPGA board by using Tina's schematic editor, programming FPGA boards with Tina using schematic design entry, and the VHDL hardware description language, programming FPGA boards in VHDL with Tina. Now, in this video tutorial, our circuit, a full adder, will be based on the Verilog hardware description language. The textual description of the hardware greatly enhances portability and reusability. By using hardware description languages describing the fundamental operations, structures, and connections, virtually any logical circuit can be defined. At the end of the video, we'll use Xilinx Vivado Design Suite and a Xilinx Basys 3 FPGA board to demonstrate the configuration of the FPGA. As we stated earlier, Tina works with schematics, but we can also place HDL macros, including VHDL and Verilog, in the design. To learn more about the HDL or Verilog macro creation and its role in the simulation, watch our video, Creating Macros from Verilog, Hardware Description Languages in Tina, Part 2. Okay, now let's see an example. A full adder using a full adder Verilog macro. Start Tina. Then open the full adder verilog.tsc from the Tina examples folder. Most digital circuits that perform addition or subtraction use full adder. This combinational circuit adds two binary digits and a carry-in to produce a sum and carry out.
This 1-bit full adder
has three inputs, A, B, carry-in,
including carry-in from a previous less significant stage of a multiple-bit adder,
and two outputs, sum, carry out. Let's check the Verilog code. Double-click the full adder Verilog macro. In the full adder Verilog dialog, click the Enter Macro button. As you can see, the full adder is described by this very simple 2-line long Verilog code shown on the screen. Close the Tina HDL editor window. You can also realize this circuit with a similar VHDL code. The circuit operates like a half adder, while carry-in value is low. Start the simulation by pressing the Dig Interactive button. If Tina is in a different interactive working mode, select Digital from the interactive menu. The mode name on the interactive mode button will change to Dig. When both inputs are low while carry-in is also low, then sum and carry out are also low. When just one input is low while carry-in is low, then sum is high and carry out is also low. When both inputs are high when carry-in is low, then sum is low and carry out is high. Now let's see what happens when carry-in is high. When carry-in is high while both inputs are low, then sum is high too and carry out is low. When carry-in is high while only one input is high, then sum is low and carry out is also high. When carry-in is high while both inputs are high, then sum and carry out are also high. If carry-in is high, then the output values change as if we had added one to the full adder. Now let's test our circuit in a real environment using the Xilinx Basys 3 Artix 7 FPGA trainer board. Now let's see how to generate the source file for Xilinx Vivado. Note, as it can be seen, this circuit is already prepared for the FPGA tool export. See our previous video, Programming FPGA Boards with Tina, using schematic design entry. Click the T&M menu and select Export to Xilinx tool. Then click Xilinx Vivado. Create a folder. We'll name our folder Designs. Then save the three files, including two .verilog and one .xdc files, into this newly created folder. To produce downloadable content, first we create the Vivado project. Start Vivado, click Create Project, click Next. Enter the project name, in our case Full Adder Verilog, then click Next. Click Next again, click Add Files. From the Designs folder, select the two Verilog files as source files, then click OK. Leave the default target language as VHDL, click Next again, then click the Add Files button to add the full adder verilog.xdc file as well. Select the file, then click OK. Click Next again. To finish project configuration, select Boards in the Default Part dialog. You can now select the appropriate board. Select Basys 3. Note, if you cannot see Basys 3 board in the list, you can choose it manually under Parts. There, you should select part the number, click Next, click Finish. Now, Vivado is initializing our project. We can check the full adder verilog.vhd file and the full adder verilog.xdc file. Click Generate Bitstream to produce configuration data for the FPGA, then click OK in the Launch Runs dialog. Now connect Basys 3 via USB with the Vivado machine and turn the board on. As soon as the Bitstream Generation Successfully Completed message appears, select Open Hardware Manager, then click OK. Next, click Open Target, then select Auto Connect. Let's finish programming the hardware. Click the FPGA part name, then select Program Device. In the Program Device window, click the Program button. You'll see the message FPGA is programmed, and the Done LED will light up on the board. Now let's see how our simulated full adder circuit works along with the programmed Basys 3 hardware. To have a closer look at Basys 3 hardware, we'll now zoom into the area of the three switches, SW0, SW1, and SW2, and the corresponding LEDs, LED0 and LED1. Start the simulation by pressing the Dig Interactive button. We'll change the virtual switches in TINA by clicking them on the screen, and at the same time we'll also change the real switches on the Basys 3 board. When both inputs are low while carry-in is also low, then sum and carry-out are also low. When just one input is low while carry-in is low, then sum is high and carry-out is also low. When both inputs are high when carry-in is low, then sum is low and carry-out is high. Now let's see what happens when carry-in is high. When carry-in is high while both inputs are low, then sum is high too and carry-out is low. When carry-in is high while only one input is high, then sum is low and carry-out is also high. When carry-in is high while both inputs are high, then sum and carry-out are also high. As you can see, in all cases, the results are exactly the same. This is a great example of demonstrating the power of simulation, since you can test and debug circuits even before realizing them, and in our case before downloading to FPGA, where if there were any issues, it would be extremely hard to find the problem. This concludes our video tutorial of programming an FPGA development board using Verilog macros with TINA's built-in digital components. Check our video Programming FPGA Boards in VHDL with TINA, where we use a VHDL component in FPGA design. For more information, visit our website, www.tina.com. Visit our YouTube channel, www.youtube.com/user/TINA Design Suite.